Substitution. Okay, good to go? Here we go. Here we go. General line reaction for what a substitution reaction is. We're going to have some type of tetrahedral carbon, yeah? The leaving group. Something that's going to leave. Leaving group, I call it LG. Most common leaving group, halogens. Basically, your leaving group must be electronegative enough to take on an extra lone pair, which usually leads to a negative charge, but not always. Halogen is best leaving group in this order. Iodine's your best leaving group, then bromine, then chlorine, and then fluorine is pretty bad. But other atom types can be leaving groups. Oxygen, nitrogen, a variety of things can be leaving groups, but require some discussion. These are your good ones, not chlorine. Okay, general line reaction. We have a tetrahedral carbon with a leaving group. We're going to have something that reacts and replaces it, substitutes it. Nucleophile, the lone pair typically. Maybe neutral, maybe an anion. I'm not showing any charges in my general reaction. Some type of nucleophile is going to replace the leaving group. The nucleophile is now bonded to the tetrahedral carbon. And the leaving group left. When it leaves, it takes on a lone pair, as shown, as stated here. It takes on a lone pair. The leaving group has been replaced. It's been substituted. It's a substitution reaction. We didn't just add something to this, we substituted. So it's not an addition reaction. Okay, let's look at an exact, precise example. We can take this alkyl bromide. Bromine is a good leaving group, potential leaving group. Nucleophile, something with a lone pair. This happens to be an anion, hydroxide. The nucleophile can replace the leaving group. The leaving group left, it took on an additional lone pair. And that's the leaving group is going to leave as bromide. Classical substitution reaction. Mechanism for this reaction. We're going to show two possible mechanisms. And then we're going to assess them and say, okay, which one makes the most sense for this reaction? All right? Now, most books, most instructors will cover what mechanism, spend about a week on that mechanism, and then move on to the second substitution mechanism. I cover both at the same time, so we can discuss them. Okay, what type of mechanism could we show here? Obviously, we got to get this is going to bond here, that's going to leave. What do we do first? Suggestions?
Kick the leaving group off.
Kick the leaving group off. Well, thank you. I'm going to do that here because it's under SN1. This is called SN2. Okay, what if it's just left? That is, these electrons leave. What does that give? That's going to give a carbocation here plus what? That arrow means the two electrons, the bonding electrons move on to the bromine as the fourth lone pair. That's a minus. We formed one of the products right there. What do you want to call that step? Leaving group leaving? Sounds like a good name for it. What's another name for it? A more chemical-like name.
Ionization of leaving group.
Yes, ionization. We could say of the LG. Ionization. Form these ions. Okay, that would give this. How do we get the other product? these electrons making a bond here. Yeah? Because over here the oxygen has 2 lone pairs, and this would have 2 lone pairs. The other lone pair is making a bond. There we go. There's a potential mechanism. Let's do a reaction coordinate diagram for this mechanism that we showed here. We start with A, which is our alkyl bromide. What do we go to next? Any type of intermediate? Organic intermediate? We made a carbocation. What type of carbocation did we make? Primary. What do you think about that? B up here. C. Where do you want to put C compared to A in terms of energy? Sigma bond replaced with sigma bond. It's not much of a difference. You'd have to get out some bond strength numbers, tables. I can't tell. I'm going to put it pretty much even. It doesn't look exothermic or endothermic. C. Okay. We're going to have a transition state leading to the cation, right? Where the bond is breaking, it's ionizing, and it's gone. There's a transition state there, yeah? Then from there, what happens? Br minus attacks. There's a transition, I'm sorry, not Br minus. Hydroxide attacks. There's a transition state making bond till we get to here. We're falling downhill, not going to take much energy, just a little bit of activation energy. Here we go. Which one's a rate determining step? Rate determining step should be formation of the cation. Will be the slow step. Hydroxide adding should be fast compared to the slow step. Of the 2 reactants, you got 2 reactants here. You got the carbon with the leaving group. Could be called the electrophile. You got the nucleophile. Of the 2 substrates, which one is involved in the rate determining step? One, both? One or both? Which one's involved in the rate determining step? Alkyl bromide? Is this involved in the rate determining step? No. This is why it's called SN1. Substitution, nucleophilic, because a nucleophile is doing a substitution. But it's unimolecular. One molecule or one reactant involved in the rate determining step. Okay? It's the alkyl bromide. Hydroxide is not involved in rate determining step. What are the consequences of that? Well, what if we doubled or tripled the concentration of the hydroxide? Would you expect the rate of this reaction to change? Why not? More hydroxide means there's going to be more chance of it attacking the other thing. Do what? But the attacking of the hydroxide is not the rate determining step. Right. So why would doubling or tripling or quadrupling the hydroxide do anything? It will not. why we need to understand what the rate determining step is. You're just wasting your hydroxide if you think you're going to make this reaction faster by using more hydroxide. I know at Gen Chem you learn concentrations may be more concentrated, more likely for the two reactants to come together, things like that. Yeah, but it depends on the rate determining step.
Why doesn't the carbocation shift to secondary?
Good question, because if it did, we wouldn't get that product.
But like, if it's more thermodynamically stable to be secondary, why wouldn't it do that? Because it's so
No,
fast.
it's a great question. Yeah, I would expect this to rearrange. First off, I wouldn't expect it to conform, because primary is bad. We haven't really talked about that yet. But you do recognize that we're showing a mechanism for that product.
Yes.
And if we're going to show a mechanism for that product, we don't want it to rearrange. But it's a very valid question, yeah.
Wouldn't bromine be at initially a higher energy state since it can ionize off? So wouldn't it, and hydroxide wouldn't, so wouldn't it A be a little higher than C?
I'd have to think about that. You may be ahead of me on that. I've never really considered that. You can tell me where you're coming from a little bit later. I'm just putting them even because, you know, before we went from pi bond to maybe 2 sigma bonds and it was more clear. Okay, do you like this mechanism? Well, is this the mechanism or should we try another? Do you like this one? Why do you like this one? Nobody doesn't have anything bad to say about this one? Thank you, yes. Primary carbocation. Have we said anything bad about primary carbocation? What have we said about them? Not good. And if we haven't said it before, you don't ever want to form primary carbocations. It's not the most reasonable thing to propose. Okay? How did John get to the parking lot? He flew. I wouldn't propose that. You're going to sound crazy. Okay? Don't propose primary cations. That's not the best thing. You can do it if you want, but it's going to look crazy. They're not that stable. Okay? I would say he walked or ran or he was carried maybe, but flew. What do you mean, in a plane? He didn't fly by himself. Okay, not good to propose here. So do we have another mechanism we could show? That is an SN1. What's the first step of an SN1? Yes, because right there I showed you an SN1. Okay, let's try another mechanism. How else could we do this? We've got to get the same products. Another way? I suggest we avoid showing primary cation, carbocation. Another way?
The hydroxide could attack, and then the bromine could be at the same time.
Okay. Have you been reading or watching previous videos or anything like that?
Yeah,
You read the book? Don't read the book. You're supposed to learn it from me. Okay? Reading the book is good. You got to just hear it from me once and then magically understand it. All right? Yes! She proposed that we take this and do what?
attack the carbon with the bromine,
Attack here
and the bromine at the same time.
and kick that off? Can you just attack a carbon and kick off a leaving group?
Yes.
We did that with bromonium ions. We attacked it and you kicked it off. It was a positive bromine or something. Yes. Is this possible? Yes, it's possible. What is that? What does this arrow movement give? It gives that. It gives both of them, right? Hydroxide makes bond to tetrahedral carbon. What does this arrow mean? Bromine is acting as a leaving group. It takes on a lone pair by this bond moving there. It gives that. Okay. Where's the intermediate there? No intermediate. If we do a reaction coordinate diagram, we went from, what is this, A? And what is this, C? We go from A to C, and what do we do? There is no B, okay? Don't get confused. There's no B. What is this here? That's the activation energy. This is just one step. There's no intermediate. This up-down is the same as this up-down. That's just a transition state leading to a product. That's an elementary step, you could call it. 2 elementary steps. This is just one step. Just one transition state. Right? Over there you had 2 transition states. Okay, which step is the rate determining step? That step. So that's only one step. Okay? 2 arrows doesn't make it different steps. It's one step, or one elementary step. One elementary reaction, if you want to call it. I don't use that term much. I just call a step in a mechanism a step. Okay, that's the rate determining step. It's the only step. So, of these, which ones are involved in the rate determining step? Both. So it's called SN2 because 2 things are involved in the rate determining step. If this is the mechanism, if you change the concentration of the hydroxide, it's going to affect the rate. All right? Either one. Because the rate determining step is this attacking this. Here it is, this attacking it. If there's more of these, it's going to be more likely to attack it. That's the rate determining step. That's an SN2. Have we seen this before? What do we call this before? Backside attack? When we attack and kick off a leaving group? Yeah, and when you do that in terms of stereochemistry, that's not so like paper 2. How do you do, when you do this, how's the stereochemistry? Well, backside. If the leaving group is forward, how's the hydroxide come in? In the back. We've done that. How do you attack carbocations? Either side. Okay? Stereochemistry we've already looked at here. It's the same stereochemistry we did with alkenes. Which, by the way, when I teach alkenes, I include stereochemistry. That's so when we get here, we know how to do it more and more. Okay, I showed you 2 mechanisms for substitution on a tetrahedral carbon. SN1, which involves forming a carbocation, and SN2, which does not. Sometimes this is called a concerted backside attack. It's like both happens at the same time. The nucleophile comes in, leaving group leaves. No carbocation formed in an SN2 substitution. Okay, knowing the details of these 2 mechanisms is a must. Kinetic studies. I've already kind of got at this. Anything new down here? Well, maybe just terminology. Let's see. Kinetic studies have shown that the rate of the above example reaction can be affected by changing the concentration of either the alkyl bromide or the hydroxide. Thus, it sounds like the rate is dependent on both of them. Since rate depends on concentration of both substrates, each must be involved in the rate determining step, yes? And the reaction is indeed bimolecular. So the kinetic evidence confirms our prediction that this should be an SN2 mechanism. We also know from experimental evidence that the rate is first order with respect to each substrate. Thus, the rate equation is second order overall and can be written as follows. The rate in units of molarity per second equals some type of constant, K, times the concentration of the alkyl bromide times the concentration of the hydroxide. They're both involved in the rate determining step, so they're both involved in the rate equation. If you double this, you're going to double the rate. If you double both, you will quadruple the rate. Yeah? SN2. What would an SN1 look like? Rate equation. You would not have that. It would just be alkyl bromide. Rate determining step is just alkyl bromide. Hydroxide plays no role in the rate determining step. Rate determining step. What does that mean? The step determines the rate? Sounds like it. Okay, so which mechanism fits the kinetic observations? SN2. All right. Okay. Another example. Let's put in some stereochemistry. If you do this reaction, alkyl bromide with R, that's R configuration, it's chiral. React it with hydroxide. Now, of course, you can't just have hydroxide. You got to have a plus, right? All right. So it may be shown as hydroxide. It may be shown as KOH. It may be shown as sodium hydroxide. It's all hydroxide. You have to be just. I'm just seeing too many students confused about this versus this. Okay? It's the same thing. Just one of them is showing the counter-cation. All right, so we got hydroxide. Obviously, we're doing a substitution reaction. Because hydroxide has replaced the bromine, which apparently was the leaving group. We made KBr. There's only two substitution mechanisms for tetrahedral carbons. That's SN1 and SN2. We've already looked at them both. Okay. What mechanism is this? Question first. I think this says is SN1 mechanism more or less likely for this reaction compared to previous? SN1, more or less likely? Why more? Because if this just ionized, you make it secondary. That's more likely than a primary, yes? So it is more likely than the previous reaction for SN1. Next question. What does it say? Basically, is the mechanism SN1 or SN2? SN1 is possible. What's the mechanism? How do you know it's SN2? Because stereochemistry is telling you the mechanism. This is R. The leaving group is back. How did the nucleophile come in? Only front. Only. S only. That is, the reaction is enantioselective. We started with one enantiomer, we have only this enantiomer now. By the way, this is our first ever enantioselective reaction. We never did it with alkenes or alkynes. Mainly because if you only get one enantiomer, that means this is optically active, yes? S only, it should be optically active. Well, you cannot create optical activity out of the blue. Well, we did not. Because this is optically active. R only. So we did not break that rule. We have not won a Nobel Prize. We have stuck with what the rule is. But you can do this. Okay? What we have here is inversion. How do you get inversion? What mechanistically, how do you get inversion? Backside attack. This screams backside attack. Since it's backside attack, what's the mechanism? SN2, concerted backside attack. If this was SN1, what stereochemistry would we expect? Racemic, what?
Because you can go to the front or the back.
If it was SN1, we would be making this as the rate determining step. Then hydroxide would attack
Front or back.
front or back. And you would get both front and back. That would be S and R. But we did not get that. We got inversion only. Inversion comes from backside attack only, and that's your SN2 mechanism. Okay? So stereochemistry can help you determine what the mechanism is. Bromine's going back, right? How does the hydroxide come in? I can't really show it here in 3D. Some hydroxide's coming in from the front, kicking off the bromine. That's why it's now forward. How's inversion obtained? Here's the same compound, R. It's R here. It's the same exact compound, just turned a little bit. Here I have the leaving group in the plane. The hydroxide comes in behind compared to the carbon. It comes in from over here. Okay? Right behind here. Now it has to come in between these groups. Kick this off. But let's show the transition state. Transition state. What's it going to look like? I'm going to draw the carbon in. Okay, that's the carbon there. The hydroxide bond is being made. Being made. There's some lifetime where it's being generated. And then over here, what's happening to the carbon-bromine bond? It's being broken. Halfway to being made, that's actually halfway to being broken. Okay? These other groups, ethyl group, okay, H and methyl. These two groups are actually eclipsed right here. That is, the H is right in front of the methyl. We'll comment on this. Charge, though. What's the charge of the oxygen here? Well, where does it end up? That's the transition state, yes? Where does it end up when it's done? Here's the carbon. This bond becomes complete. Yeah? This bond's completely broken, so the bromine just leaves. It's gone. Took a hike. Alpha group here. The H is here. And the methyl group is there. And that's R, and this is S. Charge, let's do that first. Oxygen minus, here it's neutral. What is it here in the transition state? Partial minus. Bromine is neutral, and then minus, what is it here? Partial minus. Transition state. Pentacoordinate. Pentacoordinate, 5 coordinate. Coordinate means sort of like bonded, but not as strong a word as bonded, but just things around it, coordinating with it. Carbon has 1, 2, 3, 4, 5 things around it here. A pentacoordinate transition state. I mean, is it an intermediate that has a true? No, it's not an intermediate. It's a transition state. So we don't have a Nobel Prize for having a 5-bonded carbon. It's a transition state. Okay. Also called activated complex. If you ever heard that term. Okay. It has sp2-like character. What's the bond angle between the methyl and the H here? Tetrahedral carbon, 109.5. What's the bond angle between the methyl and H here? I haven't said that yet. It's 120. The carbon here is trigonal planar. Okay? sp2-like, trigonal planar. Let's see here. Here's the carbon, and these 3 groups are sort of like this, and the bromine is here. Okay? We can pull out the model and okay, if bromine is in the plane here, bromine green coming. The other 3 groups are that way, and they're also a little bit that way, yeah? Okay? What happens is, the hydroxide comes in backside, and it's going to kick this off. But backside is straight from over there, the plane, yeah? When it comes in, what happens? It pushes these 3 groups. I'm going to break my model here. It makes them go straight, planar. See? Let's see if I can do this. See how these 3 go straighten up and now they're just a plane? That is, if it was like this. See, there it's off the board. I'm making it go flat like that. And that's supposed to be the transition state. And this is right in front of that. But those 3 are all planar, like an sp2 carbon. Okay? Now, an sp2 carbon has what left over, other than the 3 hybrids? The 3 hybridized orbitals. sp2 has what left over? Yes, a p orbital. And the p orbital is perpendicular to that plane. It's sort of like a p orbital there between the incoming and outgoing. Does that carbon look trigonal planar? If you consider the 3 things, trigonal planar, and then the p orbital. Okay, it's supposed to be that. So, how do we get here? Hydroxide comes in here. Okay, it pushes this planar. But when this departs, what happens to these 3 here? Oh, they actually do that. You see? They went that way. Now, if I did my hand here, like here, they straighten up the planar. But then, when the bromine departs, these electrons move and go, they now go this way to make plenty of room for the new group over there. That's called inversion. A lot like an umbrella in the wind. You know, it's like this over your head, You ever seen an umbrella go the other way? But between here and when it goes up like that, what transition state does it go through? At some point, it becomes straight. You may not ever see it if you blink, but then it quickly goes this way, and then it's over going the other way. Okay, it went through a planar transition state. That's called inversion. 99.9% of the time, you're going to go from R to S. You're inverting your stereochemistry. Okay, for us, it's always going to be like that. Okay. Important though, it takes on a p orbital in the transition state. P orbital light. Consequences of that. We're about out of time. Consequence of that should allow us to answer this question. If you do substitution, what's the nucleophile here? I minus? I minus replacing Br minus? Or Br? Okay? This reaction is a lot faster. This one is, you can do the math, it's a lot slower, ain't it? Lot slower. Why is it slower? Really, you should answer, why is the one above? No. You really want to focus on here. Why is this one so much slower? And then we want to look down here. Basically, some follow-up on the consequence of these SN2 transition state. Questions?
So you said it's more likely for it to go from R to S, so you can extend it to S.
Oh, or the other. 99% of the time. Inversion. That is S over there, right? That is S. Need to make sure it's S.